Our next speaker is Marika Holland. Marika is from the National Center for Atmospheric Research at Boulder. Her research interests include understanding the role of sea ice in climate systems, including understanding the ice-ocean atmosphere feedback mechanisms. She does a lot of work with coupled climate modeling, and she's done some really good work with sea ice dynamics in the climate system, and that's what she's going to report on today.
Okay. So I want to thank the organizers. This has been a really great meeting, and I'm happy to be participating in it. So I'm going to talk about Arctic sea ice and the potential for reaching seasonally ice-free conditions in the not-too-distant future. And I'd like to acknowledge my collaborators on this work, including Cecilia Bitz at University of Washington, Bruno Tremblay, who's at McGill, Mark Serez, Julian Struve, Walt Meyer, and Ted Scambos, who are all at the National Snow and Ice Data Center. So as we've heard over and over again in the last day or so, the Arctic is changing. These changes are happening in the atmosphere, the ocean, the terrestrial system, and they're also, of course, happening in the sea ice. And we've seen this plot several times in the last day or so. It shows the satellite record of the September ice extent, so from 1979 to 2005 here. And there are a couple interesting things about this time series. First is the trend. It's pretty obvious that this is decreasing. The decrease is about 8% per decade. So we've lost over 20% of the sea ice in September since 1979 when this record began. Another thing that I think is pretty interesting about this time series is that the character of some of the minimum ice years have changed. So the last 5 years, including 2006, which isn't shown here but was also a very low ice year, we've seen one low ice year after another. And this is in contrast to conditions in the 1990s where we did see some pretty low ice cover in September, but the ice then recovered a year or two later to normal or above normal conditions. So somehow the character of the sea ice loss is different now. We've sort of entered a new state. Some people have suggested that perhaps we've passed a tipping point and we've entered a new era in terms of summer Arctic sea ice conditions. In terms of where the sea ice has been lost, this shows conditions in 2002, 3, 4, and 5. The pink line here is the mean ice edge. So you can see that we've lost ice. The colored regions are where ice is present for these years. So we've lost ice north of Alaska, here in the Beaufort Sea, Chukchi Sea region, and the East Siberian Sea. And that's been pretty consistent over these years, although that spatial distribution of the changes, of course, differs from one year to the next. Understanding those observed sea ice losses is important and a very important research question. But we also, of course, would like to understand what might happen in the future. And there are several different ways in which we can try to address how sea ice might change in the future. The first is just a simple extrapolation from the observations. So this shows that observed time series of September ice extent. If we just extrapolate this into the future, using the trend over the last 10 years or so from this record, we'd expect ice-free conditions in September around 2060. If we use the trend over the whole record, maybe 2100. But of course, the climate system is not this simple. Things don't typically just move linearly into the future. So instead, we turn to climate models. And these climate models are very complex systems in their own right. They include atmosphere, ocean, terrestrial sea ice systems. All of these interact and change together. And if we look at the model simulations from the IPCC fourth assessment report, what we find is that about half of those models reach near ice-free conditions by 2100 in September. But half of them don't. And some of them actually show quite small changes in sea ice over the 21st century. And these are all in response to the same greenhouse gas forcing scenarios. So there is uncertainty in terms of when we might reach ice-free conditions in the Arctic from these climate models. Now, if we exclude models that have unrealistic present-day ice conditions, when we compare them to the observed record, the fraction of models that reach ice-free conditions by 2100 does increase. So some of the models that don't reach ice-free conditions within the next century don't reach them because they're very thick, extensive conditions in their present-day simulations. I personally think that this year at which we reach ice-free conditions in the Arctic, I mean, it's uncertain, and perhaps the more important question is not exactly when the Arctic will go ice-free, but how it gets there. We've heard discussions about tipping points, about thresholds in the Arctic. I mean, the freezing point of seawater or freshwater is a really strong threshold. And it gives us this potential for tipping points or potential for abrupt change. And some people have suggested that we've already reached tipping points in the Arctic sea ice cover. So we wanted to look at this question from the context of future projections of the sea ice. And these climate model projections are subject to gradually increasing changes in CO2, gradually warming atmospheres. So the global average air temperature increases quite gradually over the 21st century. So how does the sea ice respond to this? Well, this shows a climate model simulation over the 20th century, the black line here, in terms of the September ice extent simulated by this model. The red here are the observations. And you can see that the sea ice is relatively stable over the 20th century. There is a small downward trend, but it's quite small. And at the end of the 20th century, we have conditions shown here. This is the ice concentration in September for a 10-year average. And you can see that the Arctic remains completely ice-covered. We do have lower concentrations in the shelf regions, but the Arctic Ocean is covered with sea ice year-round. Now, in this model simulation around the year 2000, the ice undergoes some fairly rapid changes, quite similar to what we've seen in the observed record. And we have conditions by 2010 to 2020, such as those here. You can also see that it undergoes this fairly rapid reduction in ice cover, but then it stabilizes. And it stabilizes at these reduced levels for about 20, 25 years or so. So we have an Arctic which is still completely covered with sea ice. The ice concentrations are reduced. We're starting to see open water in shelf regions. But we still have a perennial ice pack. However, in this model simulation, what then happens is the ice cover undergoes this incredibly dramatic retreat. It goes from conditions such as we've seen, very similar to what we've seen the last several years in the Arctic, to near ice-free conditions in a decade. So not only do we lose the ice, but we lose it in these bursts, these pulses of very abrupt retreat. And so by 2050, we're left with conditions where the Arctic basin is essentially ice-free in the summer. There's a little bit of ice that remains along the north coast of Greenland and the Canadian archipelago. But, I mean, you can imagine the impacts that this would have on things like shipping through the Arctic. So this is a very dramatic, rapid change. Now, it's worth noting that this is what happens in September. The ice cover grows back in the winter. So we still have a winter ice pack. And we do actually see increased ice growth in the winter as we lose the sea ice. So not only do we want to look into the future, we'd like to understand the mechanisms that drive changes in the sea ice in the future. And so this time series here shows the March ice thickness. So this is, if you looked at the annual average ice thickness, it would show a very similar time series. And you can see that during this abrupt ice loss, which is shown, the abrupt ice retreat event is shown by this gray shading, we do have accompanying decreases in ice thickness. And these largely result from increases in melting of the ice, particularly at the base of the sea ice. But you also see that these decreases in ice thickness are not particularly remarkable when you compare them to earlier events, such as this one around the year 2000, or even earlier reductions in ice thickness that occurred within the 20th century. So what's different is this reduction in ice thickness results in very large changes in ice extent. And what we have happening here is that as the ice thins, it moves to this more vulnerable state. Now we have these very large regions of the ice pack, which are very thin. You increase the melting a little bit, you can completely melt out these regions and get this very large ice extent response. This relationship is quantified here. This shows the March ice thickness from the model. This is averaged over the Arctic as compared to the change in open water formation, or the amount of open water formation we get per centimeter of ice melt. So you can see that when you're at around 3 or 4 meters, the ice, of course, melts in the summer. It thins vertically, but you don't get a large open water or ice extent response. However, when you get to 1 to 2 meters in thickness, now your melting over the summer can completely melt out regions of the ice cover, allowing this very large ice area response. So that's one of the factors that's important in this abrupt retreat. Another one is the fact that we have these accelerating feedbacks at work in the Arctic. And the most dramatic of these is the albedo feedback. So when we move from a situation like this, where we have a completely ice-covered ocean, so this is Alaska here, the Arctic ice cover, to a situation where that ice cover is lost, now we start absorbing a lot more sunlight. That accelerates the melting. We absorb more sunlight, so we get into this vicious cycle. And when we look at the shortwave solar radiation absorbed in the Arctic Ocean, we see this large increase that occurs as the ice cover is lost. And that accelerates the melting and speaks to the abruptness of the change that we see. Now, there's one final factor that we've found is really important in driving these observed light, or these simulated ice loss events, and that's a triggering event. In the case of these model simulations, the trigger are increases in ocean heat transport to the Arctic. Those heat transport anomalies come from the North Atlantic into the Arctic Ocean, and they lead and occur over the simulated abrupt retreat. So we have larger heat transport into the Arctic Ocean from the North Atlantic, increases the basal melting, allows these positive feedbacks to kick in, and the ice to abruptly retreat. And these increases and the pulse-like nature of the increases in ocean heat transport that are simulated by this model, as shown here, bear some resemblance to some of the increases that are being seen in the observed record. So this shows from this study by Polyakov the increases in ocean heat transport. This is actually in temperature. As these anomalies move from the North Atlantic into the Arctic and then are circulated around the Arctic. And these warming events appear to have a pulse-like nature to them. They happen very abruptly. And that's similar to what the model simulation is also seeing. So what drives the abrupt ice loss in the simulations? Well, it's this transition of the ice to a more vulnerable state as it thins. We're definitely seeing thinning of the Arctic ice cover in our observed records. A trigger, which in the model simulations are these rapid increases in ocean heat transport to the Arctic. I think it's important to note that other natural variations, changes in ice motion, wind force motion, for example, could potentially play the same sort of triggering role. And then these positive feedbacks that kick in and accelerate the ice retreat. The surface albedo feedback is the most obvious one. We think that there are also some possibly important feedbacks associated with ocean heat transport to the Arctic and how sea ice growth and brine rejection within the Arctic Ocean might impact changes in ocean circulation and heat transport. So what I've shown you are all simulations, a single simulation from a single model. Well, how does this compare to other simulations, other models? We do have a group of ensemble members from this model. These ensemble members are run with the same model, meaning that they're subject to the same physics, the same external forcing, same changes in greenhouse gases, for example, but they're in different phases of their own intrinsic or natural variability. And if we look at this group of ensemble members, we see that all of them have abrupt events. The timing of the events, the length of the events, they vary somewhat among the models. And a typical event lasts about 5 years. But they all have these very rapid ice loss events occurring, and similar mechanisms drive the events in each case. There are many changes that are also associated with these abrupt ice loss events. One is that we see a rapid warming. So this shows the air temperature changes just after an event versus just prior to an event. We see in the December Arctic warming of something like 5 degrees in about a decade. We also see rapid increases in precipitation. This shows precipitation changes for the 2040s minus the 1990s. So there's this general increase in precipitation over the Arctic Ocean, and that's most rapid during this abrupt ice loss event. So we see about a greater than 15% increase in precipitation in about a decade associated with this abrupt ice loss event. We also see changes in near-surface permafrost and a very rapid loss of near-surface permafrost extent associated with the abrupt sea ice loss event. So there are all these associated changes, many of them affecting the hydrological cycle in the Arctic, that occur very rapidly along with this sea ice loss. As we all know, climate models have uncertainty, and the fact that this one model shows these abrupt ice loss events, I think, begs the question of whether this is a robust feature of these models or whether models differ in this respect. Well, some models very definitely do have some other models very definitely do have abrupt ice loss events. This shows the September extent over the 20th and 21st century from a French model showing this very rapid ice retreat. But other models, while they might have quite large changes in September ice cover and might go ice-free in September by the end of the 20th century, they do it in a much more gradual fashion. So models do differ on whether or not they show these sort of abrupt ice loss events. And when we look at the group of IPCC Fourth Assessment Report models, so these are the latest state-of-the-art models, we find that 50% of them simulate abrupt reductions in ice cover for some future forcing scenario, and that it's more likely to see rapid ice loss in simulations run with higher anthropogenic forcing. So why do models differ so much in terms of whether or not they show these rapid ice loss events? Well, there are multiple reasons, and it's hard to pin down just one. But one thing that definitely influences the model's future projection of sea ice conditions is the conditions it has at the end of the 20th century. So again, these are fully coupled climate models, meaning that they simulate the sea ice thickness, as shown here from 12 different models. And that sea ice thickness is subject to the heat budget that's simulated by those models, which of course is affected by ocean circulation, atmospheric circulation, cloud conditions. So it's a very complex thing to get right. And you can see that these models differ quite dramatically in terms of their sea ice conditions, their sea ice thickness, at the end of the 20th century. Some models have quite thin ice conditions, others have quite thick ice conditions. The ice thickness distribution varies quite dramatically among the models. And this, of course, is going to affect how the ice evolves in the future in these model simulations. So that's one of the things that's important, that affects whether or not these sea ice simulations exhibit abrupt retreat. And it also has an important effect on just the general sea ice projections from these models. So there is this uncertainty in climate model simulations. Not only do they differ in things like their ice thickness, they also differ in the strength of their feedbacks. They differ in their natural variability. And all of these things affect whether or not these models simulate abrupt ice loss and also just their general ice retreat simulations. I think it's important to note and try to understand this uncertainty in climate models. I think it's also important to note, though, that uncertainty does not mean that these models provide us with a worst-case scenario. The exact opposite might be true. And in a recent study led by Julian Struve, and this figure has been shown earlier in this meeting, we do see evidence that perhaps these models are not sensitive enough. So when we compare the IPCC Fourth Assessment Report models, which are all these squiggly lines here showing their 20th and 21st century simulations. Now, over the 20th century, these models are subject to greenhouse gas forcing. Some of them have volcanic forcing, solar forcing. So they're forced with our observed records of how things have changed over the 20th century. So because of that, we should be able to directly compare them to the observed time series. Well, you can see when you look at the observed time series that the rate of retreat is very rapid and more rapid than what our climate models simulate, suggesting that these models are probably not sensitive enough and that perhaps they're giving us a best case scenario of where the Arctic ice cover might go in the future. A seasonally ice-free Arctic, well, is this a question? I think all evidence, the observational evidence, climate models, they all suggest that a seasonally ice-free Arctic could very well occur within this century, by 2100. The transition to this state may actually be very abrupt, with periods of relative stability followed by very rapid change. And of course, and as other people in this room know much better than I do, this has consequences for the ability of societies and ecosystems to adapt to these sorts of changes. So this rapid transition to seasonally ice-free conditions also has numerous associated changes. Rapid warming, particularly in the wintertime air temperatures, changes in precipitation, melting of permafrost, all of these things go in line with the sea ice changes. There are, of course, ecosystem and socioeconomic impacts, and as Matthew Sturm raised yesterday, there's this changes in sea ice do affect climate outside of the Arctic regions, although exactly how and where still is uncertain, and I think is an open research question that some effort needs to be put into understanding. And with that, I will close, and
Thanks, Marika.
thank you.